Hi everyone, hope you've had a good break and you're now raring to go for our first lesson of 2020, which today will be on absorbed dose. So learning intention for today, to explore the relationship between absorbed dose, energy and mass, and hopefully by the end of the lesson you'll be able to explain what is meant by the term absorbed dose, be able to state an equation linking absorbed dose, energy and mass, and of course you'll be able to perform calculations involving these three quantities. So start off with a little bit of revision. First of all, what is an alpha particle? Well, an alpha particle, obviously alpha being the first letter of the Greek alphabet, alpha particle is made of 2 protons and 2 neutrons, the same as a helium nucleus. So here we have an alpha particle here. Now an alpha particle can be absorbed by a sheet of paper or a few centimetres of air. So there we have our alpha particle being absorbed by our sheet of paper. The beta particle, of course, is a fast-moving electron, beta, of course, being the second letter of the Greek alphabet. So here we have our beta particle. It is our, as I say, our fast-moving electron. The beta particle is absorbed by a few millimetres of aluminium. So here we have a beta particle, obviously moving much faster than our alpha particle because it's a fast-moving electron. It's much smaller, much lighter, and in this case it's absorbed by our aluminium sheet there. So finally, a gamma ray. Now, gamma ray is of course a type of electromagnetic radiation. It's part of the electromagnetic spectrum. So here we have a little gamma ray here. Gamma rays need a few centimetres of lead, so something quite dense, some sort of dense metal such as lead, to be able to absorb them, or several metres of concrete, so it takes quite a lot for them to be absorbed. So here we have some lead, and of course the gamma rays move very, very fast because they're travelling at the speed of light. Finally, activity. So if you remember, activity is how many nuclear decays are happening every second. So remember, nuclear radiation, this is just a little aside, nuclear radiation is always emitted from the nucleus of the atom. So here's our equation for activity. So A, obviously standing for activity, measured in becquerels, is equal to N, the number of decays, divided by time, which is measured in seconds. Okay, so now on to our new material. So if too much nuclear radiation is absorbed by living tissue, obviously it can cause an issue, but we know this is something that's kind of fairly well known. So we obviously need a way of measuring just how much nuclear radiation has been absorbed by a sample of tissue or by indeed a person or an animal. So this is where absorbed dose comes in. Absorbed dose is the amount of energy that's absorbed per kilogram of tissue. Okay, so it's the amount of energy that's absorbed by each kilogram of tissue. Now, absorbed dose is measured in a unit called Gray, which is abbreviated to capital G, small y. Okay, so what's our equation then? Well, this is our equation here. D, obviously, as we've said already, stands for absorbed dose as measured in grays. E is our energy, which is measured in joules, as always, and M being our mass, which is measured in kilograms, as always. So that's our equation there, nice and simple. Absorbed dose is equal to energy divided by mass. D equals E divided by M. So let's have a look at a worked example then. If we have a tissue sample of mass 2.3 kilograms, which absorbs 120 joules of energy from a radioactive source, we are asked to calculate the absorbed dose here. So, first thing we do, as always, I'm sure you've already got there, we're going to write down our shopping list. Now, in order to do a shopping list, I'm just going to highlight some key information in the question here. So we have mass 2.3 kilograms, we have energy 120 joules, and we're being asked to calculate absorbed dose. So let's put these three quantities here into our shopping list. So we have now our mass, M equals 2.3 kilograms, energy E is 120 joules, and D, our absorbed dose, is what we're looking to calculate. So we put that down as a little question mark. So for our first mark, we can now write down our equation. There we go. D is equal to E divided by M. That gets us our first mark. We're now going to get our second mark just by substituting in these numbers. So where I see E here, I'm just going to substitute in E here. Where I see M, I'm going to substitute in the number for M. So that gives me D is equal to 120 divided by 2.3. So I calculate that out, I come out with a number here, 52.1739, and there's various numbers after that. So of course we need to round that off, so round that off to D equal to 52 joules. Now rounding that off to two significant figures gets me my third mark. Obviously we want to use two significant figures here, because if we look at the numbers that are given to us in the question, mass is in 2.3, that's two significant figures, and energy 120 joules, that's also two significant figures. So our final answer we want to give to two significant figures. So that's 1 mark here for our absorbed dose, 1 mark for 1 mark here for our equation, 1 mark for plugging in our numbers, and 1 mark for our correct answer, rounded to the correct number of significant figures and with the correct units. Okay, so now it's your turn. I'd like for you to have a go at the problems below. So this is page 34 of the Waves and Radiation question booklet. If you've not got a copy of that, I'll make sure there's a copy on Google Classroom, so you can go and find that on there. Along with the answers, I'll make sure that the answers are on Google Classroom as well, so you can check your answers as you're going through it. So page 34, questions 6A only, 7, 8 and 15A. Okay, now there's various other questions in here which include something which we'll be looking at next time we're in. So I don't want you to do any of those ones. So in particular with question 6A, it's just the first kind of for first 3 columns up to the absorbed dose. Don't worry about any of the other ones where you're looking at the alpha particles or equivalent dose or anything like that, radiation weighting factor. Just ignore those final columns in that question there. Remember to check your answers against the answers that are in the document in Google Classroom. It will be available on Google Classroom, and if you don't understand something, ask in the comments. I will be online during our normal scheduled class time to answer any questions you might have. So just to finish off then, our success criteria. Hopefully by now you can now explain what is meant by the term absorbed dose. You can state the equation which links absorbed dose, energy and mass, and you've been able to perform a few calculations involving absorbed dose, energy and mass. Okay, as I've said, any questions, if you're not getting something right, ask in the comments in Google Classroom, or send me an email. You'll be able to should be able to send me an email via Google Classroom as well, and I will get back to you. As I say, I'll be on. I'll be monitoring my emails and monitoring the comments during the scheduled class time. So that's from 1:15 until 2:05 today, Monday the 11th of January. Okay, hopefully you got on okay with that. As I say, any problems let me know, and I will see you next time.